All right, so the next natural question is, what if the numerator is not constant? What if it is linear? So I have 2x plus 5 over x squared plus 6x plus 11. Crucially, something down here that does not factor, because if it did factor, I would use integration by partial fractions, which is, long, but it's, it would work better. All right, so here's number 2 from this. So the technique, I actually call this technique forcing q prime. I sort of made that up. It doesn't really have a name. What I mean by that is if you have, p over q, all right, what you're always looking for is q prime over q, because q prime over q is du over u, and when I integrate that, I'm going to get ln, right? ln of absolute value of u. All right, this is just some scratch notes up here. So if, p over q is my general rational expression, if I can get the top to match the derivative of the bottom, right, then find a du over u form. All right, this one, I don't have a du over u form at this point, but crucially, I do also want to note that, what is going to make me go toward this technique of forcing q prime. I notice that the numerator is linear, the denominator does not factor. So that's what tells me I'm going to use this technique, forcing q prime. All right. You might have noticed there's a lot of different techniques that are regulated by what the sort of criteria of each problem are. Next week, we're going to mix them all up and you're going to decide the technique. So what will be useful for you is this summary of rational integrations. And it just tells you, I wrote out a 5-step procedure to examine each aspect of this integral. So, if we were looking at this, we would say, is the degree of p greater than the degree of q? No, so I'm going to skip that step. Do I have kq prime over q of x? Well, if I did the derivative of this 2x plus 8, I don't have 2x plus 8. If I double it, I have 4x plus 16, not 4x plus 12. So I don't have that. All right. So does the denominator factor? If it does, I use partial fractions. All right, but it doesn't. So that pushes me to step 4. Denominator is quadratic, does not factor. Numerator is constant. Okay, but I don't have that. It's linear. Denominator is quadratic, does not factor. Numerator is linear. Then we're going to do this. Separate the numerator into a multiple of q prime and a constant. That's going to be the technique that we call forcing q prime. All right, and I wrote all of this up into a nifty flow chart. All right, which all of this I will post it today, but I would say don't get too involved in this today. You might want to look it over because it's a good sort of summary. That's why it's called a summary. It's a good summary of the techniques that we'll have done by the time we finish this. And next week, I'm going to scramble all these together and let you figure out which technique to use. All right. So the only reason I'm talking about that is because how do we know we're going to do this technique forcing q prime? Because the numerator is linear and the denominator does not factor, and I don't have q prime over q. Not yet anyway. All right, but that's the idea, is I'm going to force it to be q prime over q. So let's say, I should check to see if I can use a u substitution anyway. So if I did do a u substitution, what would the u be? It would be the denominator, x squared plus 8x plus 25. Then what would the du be? It would be 2x plus 8 dx. So the first thing I should check is, can I just multiply by something and get that? Can I do, I could do 2x times 4. So, I could do 2x times 2 and get that 4x. So I could go 2 du equals 4x plus 16 dx, but it still doesn't match. All right. But as long as I can get the x to match, I can rewrite the integral so that I do have something that matches. So what I can do is I can say, they say you have to integrate the rational expression that you have, not the rational expression you wish you had. But I wish I had this rational expression, so I'm just going to say that's what it is. 4x plus 16. That sounds so cheaterly. I'm just going to, if you believe something, it's true. See, that was a 25 down there. If I just wish hard enough that 12 was a 16, it is a 16. All right, but how can I allow that to happen is I can allow that to happen as long as I say, well, it's really 12, so I'll go minus the integral of negative 4 over x squared plus 8x plus 25 dx, all right? So this integral is not the same as this integral, but these integrals together, that's a plus right there. These integrals together, if I go 4x plus 16 plus negative 4, yeah, they do combine to make 4x plus 12. The denominator will be the same, and I can combine the integrals. if this was a definite integral, I would make sure that the limits matched. All right, but you would do that because you're taking a given integral and you're splitting it. So if I had limits here, I would just put the same limits on both of them. All right, so that's what you do. You basically split up this integral. All right, and then we can do this one by u substitution, and we can do this one by completing the square, but I'm going to avoid this video running to 10 minutes and start the next video.